This is the first part of a three-part series. We're going to start talking about nuclear chemistry for this unit. As you can probably guess, this is the chemistry of the nucleus. So let's get started. Previously, this year we've talked mainly about chemical reactions, okay? So chemical reactions, we've really focused a lot on the valence electrons in the atom and how they're changed. We have learned that elements and atoms can be rearranged to form new compounds. In general, the law of conservation of mass is obeyed, and some energy can be either absorbed or released, and we say that it's a little. That's mainly in comparison to what we're about to talk about. So in this unit, we're talking about nuclear reactions. These are very different. The changes occur in the nucleus. That's what the name nuclear reactions means. It involves protons, neutrons, and electrons in the nucleus, so no valence electrons are involved. Rather than elements and atoms being rearranged to form compounds, we have something called transmutation occurring. And transmutation is when one element is changed into another. That should sound a little strange. We've said that that can't happen. It doesn't happen in a normal chemical reaction, but it does happen in a nuclear reaction. The law of conservation of mass is not always obeyed. Mass can change into energy and vice versa. And the energy changes associated with this are very, very big. Like they don't even compare to chemical reactions. The amount of energy produced equals mc squared, and if you think earlier in the year we talked about c, it's the speed of light, 3 times 10 to the 8th. So if you imagine that squared and then multiply it by the mass that you're changing into energy, that's the amount of energy produced. So it's a very, very large amount. So my pictures here kind of represent that. A chemical reaction might be something on the order of a campfire, whereas a nuclear reaction is something on the order of the sun. So it's a lot more energy. We're going to talk a little bit, not much, about the history of radioactivity. The first person who really discovered radioactivity was Henry Becquerel. He was studying something called phosphorescence, which is a fancy word for glowing, and he was studying it in uranium ore, which is basically a rock of uranium that isn't pure, so it contains some uranium. And he discovered by studying phosphorescence that if you expose uranium ore to things like sunlight, that it'll glow. Well, through his studies, he actually discovered that you didn't have to expose it to sunlight first, that it emitted radiation even when it wasn't exposed to light. So there was some sort of natural occurrence going on in the uranium ore that was emitting energy, radiation. Okay, that was the first real discovery of nuclear energy. The people who continued his experiments were the Curies, and they eventually worked together. They further experimented with that uranium ore, and again, that's a mixture of several different substances containing uranium as only one component. They isolated the uranium and determined that it was the substance with those unique properties, and they called those properties radioactivity, or radioactive, meaning a substance that gives off rays of energy from the nucleus. And together with Becquerel, they won the Nobel Prize because this was previously completely unknown. Radioisotopes are a term that we're going to use for isotopes that do this. They basically have unstable nuclei that will decompose and produce or release particles in the process. So some of those particles that they release are called alpha particles. This is the symbol for alpha. It's the Greek letter. Beta particles, that's the symbol for beta. And those are actually particles that have mass. Something else that's frequently emitted is gamma radiation, which is energy. It's not a particle. You might remember that gamma radiation is one form of electromagnetic energy. So it's just energy, it's not mass. And these are just the most common. Another term that you'll hear instead of radioactive isotope is radioactive nuclide, and that just refers to the nucleus of a radioactive substance. So let's look at alpha decay. Basically, one of the most common ways that nuclei that are unstable do become stable is by releasing a particle called an alpha particle. An alpha particle is made up of 2 protons and 2 neutrons. So that's what it's made of. And there's a little picture of one. So it's 2 protons, 2 neutrons. So we have the 2 yellows and the 2 blues to represent that. If you think about it, if it's got two protons, it's essentially a helium, okay? With two protons and two neutrons, but we really just refer to it as a helium nucleus because it doesn't have the electrons that you would normally find in helium, okay? So the symbols that we use for an alpha particle, one of them is, again, that He symbol for helium, and we put a 4 on top and a 2 on bottom. Now, it's been a while since we did this, okay? But that top number there is the protons plus the neutrons, and the bottom number is just the protons, okay? So 4 and 2, 4 means 2 protons, 2 neutrons. The 2 on bottom means just the 2 protons. Another equivalent symbol that we sometimes use for alpha particle is the alpha symbol with that same 4 and 2. Now, because we are losing protons, the element actually changes, okay? A new element is formed, and this is that fancy word transmutation. So in this example up here, element Sg, which has 106 protons, it loses 2 of them. So Sg, which is seaborgium, actually changes into element 104, which is rutherfordium. So we have kind of like alchemy, okay? We have one element changing into another because it loses it. Alpha radiation isn't actually very powerful compared to other types of radioactive decay. It can be stopped by something as simple as a piece of paper. And again, this is a very common type of radioactive decay, especially for very heavy elements at the bottom of the periodic table. Another type of radiation is beta decay. So again, this is a particle that's being emitted, and this is when an atom loses an electron from the nucleus. Now, this is a little bit more complicated than what we're going to get into, but you might be wondering, how does it lose an electron from the nucleus? I learned that protons and neutrons are in the nucleus. There's no electrons in the nucleus. Well, here's kind of the strange situation. A neutron in the nucleus converts into a proton and an electron, and then the electron is lost. Okay, so here in this diagram over here, the white circles represent neutrons. So we see that a neutron breaks apart into a proton and an electron, and then the electron is ejected. That's the beta particle. Okay, what that leaves behind now is a new proton. So because we have a new proton in the nucleus now, again, you are changing the element. So cesium changes into barium. That's an increase in the number of protons from 55 to 56. That's hard to read, but that barium there is 56. So again, the symbol that we use for this, we can sometimes use a E minus for electron because that's basically what it is, or we can use the beta symbol. Now, as far as the numbers go, remember that the top number is protons plus neutrons and the bottom number is protons. Well, an electron isn't really a proton or a neutron, so this gets a little interesting. The bottom number is supposed to be the number of protons, and an electron is the opposite of a proton, so we put a -1 on the bottom. Okay, the top number is the protons plus the neutrons. We don't have any of them, so we put a 0 on top. So either of these can be the symbol for a beta particle. And again, the bottom number, the atomic number of the element, the number of protons, increases by 1. The top number doesn't change at all because the electron that's being lost is very small. The final very common type of radiation that we see is gamma radiation. And again, this is not a particle. This is simply high energy photons. So remember, photons are little packets of energy that are ejected from the nucleus. This usually goes along with and accompanies other nuclear emissions, and it represents the extra energy that's lost when the nucleus becomes stable. It doesn't change any of the particles in the atom, so the atomic number or mass doesn't change. It's not affected by this. This is very difficult to stop, and it requires several centimeters of lead or several feet of concrete to stop it. Okay, so just like radio waves, travel through the walls of your house to get into your house and, turn on the radio. Gamma radiation is the same way. It can travel through objects, and it takes a lot to stop it. Again, this is showing the relative strength of the particles. Alpha can be stopped by like a piece of paper. Beta takes something a little bit more dense, like a piece of foil. Gamma requires something very thick, like lead or concrete, to stop it. All right, a little bit of vocabulary terminology. The first thing to think about is the nuclear mass defect. Now, this might be a completely foreign concept to you. The main idea is that you would think if you take 3 protons and 3 neutrons, and you put them together into a nucleus, that 3 protons plus the 3 neutrons would equal 6. Okay? The sum of the component parts should equal the total mass of something. Well, what we find in the nucleus of an atom is that the total mass is always smaller than what we would expect. So there's some missing. So that's what the defect or deficit is. Okay, the mass is smaller than what we predicted. And the main idea here is that that lost mass has been converted into energy. So how much energy? The amount of energy that's produced is called the nuclear binding energy. And again, it's literally the binding energy. It's the energy needed to hold the nucleus together, and it came from the lost mass. The amount of energy produced equals E equals mc squared. So again, the mass is the deficit. It's the missing mass, and it's multiplied by the speed of light squared. So it's a lot of energy produced. Now, this is the energy that holds the nucleus together. We need to make sure we understand why does the nucleus need energy to hold it together? What's the big deal? Well, if you think about what's in the nucleus, you have a bunch of protons and you have a bunch of neutrons that have no charge. Okay? Do these protons want to be in a very, very close proximity to each other? Not really. We know from Coulomb's law that like charges repel. So these protons don't want to be close to each other. So in order for them to get really, really close together like they are in the nucleus, we need energy to hold them there. So that's the nuclear binding energy. And again, we get it from the lost mass. Finally, the force that holds them together is called the strong nuclear force. This is the created from the energy that holds those protons together. Okay, it prevents them from repelling and basically leaving each other. Okay, it acts over very short distances and overcomes those positive repelling forces. This is one of the 4 what they're called like fundamental forces of the universe. One of them is gravity, one of them is electrostatic forces, and one of them is the strong nuclear force. Now, this struggles when we get into the very, very large elements at the bottom of the periodic table. So that's why those large elements are relatively unstable. That strong nuclear force just can't hold them together. Now, nuclei that are not stable, so like the really, really large ones or ones that have a certain ratio that's out of whack, are not stable, and we say that they undergo radioactive decay. So again, they release those particles from the nucleus. And if it's spontaneous, that is again the result of the instability of the nucleus. So what causes stability or instability in the atom? It's the ratio of neutrons to protons. Okay, so if that ratio is close to 1 and you're in a small element, so like close to the top of the periodic table, if it's a 1 ratio, it's likely to be stable. So carbon 12 is an example. Carbon 12 has 6 protons, 6 neutrons. So of course 6 to 6 is a 1 ratio. So carbon 12 is the stable isotope of carbon. If you have carbon 14, which has 6 protons and 8 neutrons, that is not a 1 ratio. That would be a 4 to 3 ratio, or 1.33 if you put it in decimal form. That's an unstable isotope of carbon, so it's going to undergo some sort of change to become stable. Helium-4 is 2 and 2, so that's another example of a stable ratio. For larger elements, as you get towards the middle of the periodic table, the ideal ratio changes and it's closer to 1.5 to 1. So that's 1.5 neutrons for every proton. So you need more neutrons. So xenon 132 has 54 protons, and it has about 1.5 times the number of neutrons. So that's approximately 1.5 times the number of protons. That makes this a stable isotope. Here's a visual for you. The red dots here represent stable atoms. So let's look at what the axes are to make sure we understand. The x-axis is showing the number of protons. So down here we have really small elements like hydrogen and helium. And up here we come close to elements with 100 protons. So we're getting towards the bottom. Fermium, mendelevium, nobelium, and so on. So we see that and also this line right here, this red line, is that 1-to-1 ideal ratio. Okay, so we see for these small elements, the red dots are really close to that line. So, and the red dots represent stable isotopes. So those red dots are really close to that 1-to-1 line. As the elements get bigger, we see that they're farther away from that line. So the ratio is increasing. It's closer to 1.5 to 1. And eventually we get to this point right here that's worth noting. There are no red dots beyond this point. That means that there are no stable isotopes beyond element 82. Okay, and we'll talk more about that later. Okay, so now we want to talk about what type of decay is going to happen. I mentioned earlier, or no, this is new. Nuclei with a high ratio, so if they're above the band of stability, so let me show you. We're talking about elements like up here, above the band of stability. They're going to tend to undergo beta decay, so they're going to lose a beta particle. Nuclei with low ratios, if they're below the band, are going to undergo something called positron emission or electron capture, and those we haven't talked about yet. We'll get to them. And nuclei that are just really, really big, above 82, tend to undergo alpha decay. So let's talk about those two types that we haven't mentioned yet. Electron capture is exactly what it sounds like. The nucleus is going to capture an electron from the electron cloud. It's usually going to be a low-level electron from like the 1s or 2s levels, okay? The electron goes into the nucleus and combines with a proton and converts into a neutron. The mass number stays the same, but the atomic number decreases since a proton was converted into an electron and lost. Positron emission, we haven't really talked about what a positron is yet. It's essentially an opposite electron, okay? So it's the same mass as an electron, very, very small, but with a positive charge, okay? So the symbol for it is like a beta particle because it's like an electron, but it's positive on the bottom instead, okay? So it's lost. Positron emission, the positron is lost, and that is essentially kind of like losing a positive charge. So it's like losing a proton. Those are natural changes. We can also have artificial nuclear changes. One type is called neutron bombardment, which again is exactly what it sounds like. You can bombard a neutron into an atom and sometimes it will stick. Sometimes it'll stay in there. So if we take calcium 40 and shoot a neutron at it at a very high speed, it can gain that neutron. So we see the top number is increasing, but the bottom number is staying the same. So it's still the same atom or the same element. This is used to create synthetic isotopes larger than uranium. So any element beyond uranium on the periodic table was man-made by shooting particles into an uranium atom and making a bigger atom. So here's a summary. If you want to pause, you can study this table, but this is just a summary of what we've looked at so far. And now we're going to do some examples. So we're going to write a balanced nuclear equation. So a nuclear equation is like this. You know, we've seen a couple examples of these. We just haven't done any yet. It shows the element that you start with. That's called the parent element. The element that you end with, that's called the daughter element. And there's either a particle on the reactant or the product side. So we're going to write a balanced equation for the alpha decay of thorium-230. So thorium-230 starts as TH, and the number after the hyphen is always the top number, so that's 230. And then thorium, if you find it on the periodic table, is element number 90. Okay, so this is our parent element, thorium-230, and it's going to undergo alpha decay. So that means it's going to release an alpha particle. So I'm going to put an alpha particle on the product side, so 42 alpha, and then this is like baby math to figure out what the product is. The top number is 230, but we lost 4. So big surprise there. It's 226. Okay. Bottom number started at 90, but we lost 2 on the bottom. So it's 88. And now we need to figure out what element it is. What is our daughter element? Well, it's whatever element 88 is. So if you look at the periodic table, we see that that's element Ra, radium. So this is an example of transmutation. We've changed from thorium to radium through alpha decay. Next, we want to write a balanced equation for the beta decay of zirconium-97. So again, you start with your parent element, that's Zr, zirconium-97. You have to check the periodic table to see how many protons it has. Zirconium has 40, so that's our bottom number. Now it's going to undergo beta decay. So again, decay means that you have a product. So a beta particle is our product. That's beta 0, -1. Remember, it's kind of like it's basically an electron. It's very small. That's what the 0 on top means, and it has a negative charge. And then we figure out what our product is. Notice that the top number lost a 0, so that's nothing. 97 equals 0 plus 97. So basically the top numbers have to equal each other on either side of the arrow. Now the bottom number, my students mess this up all the time, even though it's very easy math. What number has to go over here so that that number minus 1 equals 40? All the time I have students write 39, but that's not right. Think about it. It's 41. Because 41 with the minus 1 on this side is going to equal 40 on the other side. So element 41 is going to become NB. So that's our product. Okay, a couple more. Nuclear equation for oxygen 15 undergoing positron emission. So we start with our parent element, oxygen 15. And oxygen, of course, has 8 protons. Again, this is an emission, so the positron is on the product side. So that's beta symbol, 0 with a positive 1 on the bottom. And then we use that to figure out our daughter element. So 15 equals 0 plus 15. 8 equals 1 plus 7. Okay, so 1 plus 7 equals the 8 on the other side. So this element is nitrogen. Next, determine what type of decay occurs when thorium-231 undergoes some sort of decay to form protactinium-231. So this one's different. We now know the parent and the daughter element, and we're figuring out what else is going on. We're filling in the blanks. So we start with thorium-231. And again, thorium was element 90. We don't really know what's happening, but we know it forms protactinium, which is element PA. It's right next to it. PA 231. And protactinium has a number of protons of 91. So we're just figuring out what is over here because it was decay, what numbers need to go over here, and therefore what element need to go over here so that this works out. So notice that the top number didn't change, so there's a 0 right there. But the bottom number, 91 plus what, is going to give me 90 on the other side. It has to be a negative. So that means this must be a beta particle that's lost. So this would be beta decay. All right. Again, we can fill in the blanks here. It's just baby algebra. Element PM with a 142 becomes element ND with a 142, so the top number didn't change, so it gets a 0. And then we ask ourselves, 61 plus what is going to give me 60 on the other side? It has to be a negative 1. So 0, negative 1 is an E. That's an electron. Okay? So this would be electron capture. And then one more. We know that this is alpha decay. We're just trying to figure out the parent element. So again, the top numbers just add up. 4 plus 222 gives me 226. Same with the bottom numbers. 86 plus 2 gives me 88. And so element 88 on the periodic table is Ra. So radium is turning into radon, and this was alpha decay. All right. A decay series is just a concept to understand. This is a series of radioactive decays that begin with an unstable nucleus and end with a stable nucleus. So this one actually starts up here with uranium-238, and it ends down here with an element with a number of protons of 81. So that would be Tl tellurium. So that's, no, sorry. One more, 82. That green one is the final one. So it ends up being element lead. So again, it's just a series of alpha and beta decays that get us from point A to point B, from an unstable nucleus to a stable nucleus. So that's the end of part 1. Thanks for watching.